So AMC10 number theory. First, let's get into something a bit basic, powers and approximations. So in number theory, you need to learn how to approximate things, especially give like upper or lower bounds on them. So like for one, you also want to memorize a few small powers. Like you should probably know your powers up to like 2 to the 10th, for example, and 3 to the 5th. That way you can save a bit of time. And in the AMC10, time does matter because you only have about 3 minutes on average for each question. Sounds like a lot, but the problems can get pretty hard. So yeah, main tricks you'll see for the most part, 2 to the 10 is about 10 cubed. This is one that you'll use a lot because they are really close and you see powers of 2 often. Some of you may remember that problem I did involving comparing like, what was it? 2 to the 56, 5 to the, I don't remember the exact numbers, 5 to the 24, 3 to the 35, and 11 to the 16. Yeah, you'll see some of those types of problems on the AMC10 where you have to approximate things. So here's a quick example problem. Decimal representation of 1 over 20 to 20. How many zeros does that start with? Does anyone have any ideas how to do this problem? No? Well, let's think about this. Let's first think about what 20 to the 20 is very close to. What's a nice way to write it? Does anyone want to share any ideas? Oh, there's stuff going on in the chat. Oh. Okay, I guess I'll just explain how to do this problem. Basically, a main idea is that you want to approximate this denominator as a power of 10. So first you write 20 to the 20 as 2 to the 20 times 10 to the 20. 2 to the 20 is about 10 to the 6th. It's just over that, which is important. So basically you get 20 to the 20 is just a tiny bit greater than 10 to the 26. In which case 1 over 20 to the 20 is just a bit less than 1 over 10 to the 26. Now what does this latter number look like? Looks like 0.25 zeros and a 1. And anything less than this number will have 26 zeros, followed by what's probably a 9. So that tells us there's 26 zeros after the decimal point. Does that make sense to everyone? Okay, let's move on to the next problem then. Oh, wait, not problem, instruction. So you also see a bunch of divisors in number theory. So like, for example, the divisors of 24 are 1, 2, 3, 4, 6, 8, 12, 24. You'll want to know how to count the number of them really quickly. You'll also want to know how to get their sum quickly. So I'll explain that. Yeah, there's a lot to take in on this page, but I'll try to break it down. I'll use these all with 24 as an example. So 24, that's 2 cubed times 3. We write this as 3 to the 1. The main idea is that there are 4 ways to choose the power of 2 in a divisor, because it's 2 to the 0, 2 to the 1, 2 to the 2, or 2 to the 3. So that's 3 plus 1 ways to choose the power of 2 in a divisor. And there's 1 plus 1 ways to choose the power of 3 in a divisor. So in total, that's 8 different divisors. And indeed, you can see this if you list out a sort of table. Let me try to do that. If you list out this sort of multiplication table, it generates all the divisors of 24, if that helps. What's going on in chat? Okay. Let's see. Then you want this, let's say you want the sum of the divisors. Well, that's slightly different, but the main idea is, why do you get this mess? Well, let's see what happens when you expand it. Let's go back to example 24. This would be 1 plus 2 plus 4 plus 8 times 1 plus 3. And when you expand this, you'll notice that every single divisor appears exactly once, because it's a product of some power of 2 and some power of 3. So an example of 24, this first part is 15 and the second part is 4. So the total sum will be 60. That way you don't have to go through adding all 8 of them. The next thing I want to talk about is the Euler-Totient function. It's called phi of n. This thing's pronounced phi. Basically, first of all, relatively prime to n means that, if 2 numbers are relatively prime, their greatest common divisor is 1. So how many numbers that are under n are relatively prime to n? That's what the Euler's totient function answers. And in this case, the reason why you get this is basically 1 over p of the numbers are divisible by p. So 1 minus 1 over p of all these numbers are not divisible by p. And the same holds for every other prime. That's how you get this. For example, with 24, you get 24 by 1 minus 1/2 by 1 minus 1/3. This equals 8. And you'll see that there are indeed 8 such numbers. That are below 24 and relatively prime to 24. As you can see below, I've also used 60 as another example if you want to read through these. And keep in mind that this sum trick is adjustable, which means that let's say you want to find the sum of the even divisors as said below. All you need to do is remove the 1 from the sum of powers of 2, because that removes all the divisors that have no factor of 2 in them. Are there any questions about this trick? No questions? Okay. Let's move on to this quick problem. A positive integer divisor of 12 factorial is chosen at random. The probability that a divisor chosen is a perfect square can be expressed as this fraction. So how can we try to find this probability? Does anyone have any ideas?
You can first prime factorize 12 factorial.
Good, yeah, you can prime factorize 12 factorial. I just realized I put that later in the slides. That might have not been a good idea. But for something this small, you can just say 1 times 2 times 3 times 4 times, etc. And then you count the number of factors of each prime. So first you start with 2. How many factors are there? Yeah, I'm gonna skip the counting. 10 factors of 2, 5 factors of 3, 2 factors of 5, 1 factor of 7, and 1 factor of 11. Okay, now what? So first of all, the way you want to write this probability, that's just number of square divisors over number of total divisors.
We can find the number of squares we can make with these numbers.
How do you find the number of square divisors?
By making an even exponents.
Good.
Yeah.
So basically my idea is, first of all, let's do total divisors. That's pretty simple, using the trick that I said earlier. That is a 5, that is not a 6. Okay. So the total number of divisors is 11 times 6 times 3 times 2 times 2. I'm going to give you a tip. Never expand that. Always wait to see what the numerator is so you can cancel factors first. Anyways, on to the number of square divisors. This trick doesn't work because it counts a bunch of non-square divisors. But we can do something similar. The main idea is how many ways are there to pick a power for 2? Because any square divisor has only even exponents in its prime factorization. So those exponents would be 0, 2, 4, 6, 8, 10. That's 6 of them. And then for 3, you can pick 0, 2, or 4. That's 3 of them. For 5, there's only 0 and 2. So that's 2 of them. 7 and 11, you can't have any factors of them. So that's our fraction. Let's simplify it. And you're left with 1 over 22. The sum of the top and bottom is 23. Let me put out the solution in text. So are there any questions? Yeah, I just want to mention, you can also use the same trick, for example, to find the sum of the perfect square divisors, in which case you just do 1 plus 4 plus ... plus 2 to the 10th, where you take every other power, and then 1 plus 9 plus ... plus 81 times, etc. Anyways, next we'll talk about modular arithmetic. Some of you may know it as clock arithmetic. Basically, my idea is you do everything and then divide it by this number and take the remainder. So for example, here's 3 times 5 is 15. When you divide by 7, it leaves a remainder of 1. How you would write that? 15 is equivalent to 1 mod 7, or you can just write 15 equals 1 mod 7. Oh, Jeffrey is confused. Jeffrey, when you say you don't understand any of this, does that mean what's on the slide right now or the previous problem? Oh.
Jeffrey, you may need to study some of the topics. So that's why I posted the slides ahead of the class. I recommend you to preview the slides going forward and bring question to the class instead of just saying, no, I don't know anything. So bring specific questions after you preview the material.
Okay, first of all, I assume everyone gets like the concept of this. Basically, it's like clock arithmetic, which like adding times on a clock, except you can multiply them as well and stuff. So it's basically like doing everything on a clock. except it doesn't necessarily have 12 numbers on it either. Just to make sure everyone's understanding, what's 2 times 6 mod 4? That's a 6. I cannot write. That just looks worse. 2 times 6. Everyone put in the chat. What's 2 times 6 when you take it mod 4? Oh yeah, just mods are basically, they're normal arithmetic, but you just take everything mod something. So yeah, in this case, 2 times 6 is 0 mod 4 because it's 12, and then you take that mod 4 and you get 0. Keep in mind that you can also reduce numbers in the middle of your computation. So you can write 2 times 6 mod 4 as also 2 times 2 because 6 is 2 mod 4. And this will also give you 0. So that's why modular arithmetic is powerful, because it means you can reduce problems. Basically, it's similar to the trick that you used to say, what's the last digit of 17 times 52? You're just taking 7 times 2 mod 10. Now, how do you divide by numbers in modular arithmetic? Well, you have an inverse. Basically, the inverse of A is a number such that when you multiply to A, you get 1. So for example, 3 times 5 is 1 mod 7 as shown above. So 3 and 5 are inverses mod 7. If you want to take, say, 4 over 3 mod 7, that's equivalent just to 4 times 5 because it's 4 times 1 over 3. And this would equal 6. Just to make sure everyone's still following along, what's the inverse of 4 mod 9? Basically, you want the number such that when you multiply to 4, you get something that's 1 mod 9. It might take a bit of guessing and checking to find what it is.
I didn't really understand the inverses.
Oh, sorry. Basically, the inverse of a number, A, for example, that's just the number C such that AC is equal to 1 in whatever mod we're working with. So in this case, 1 over 4 is the number such that when you multiply by 4, you get 1 mod 9. I should mention you can also use negative numbers in modular arithmetic, like -2 equals 7 mod 9, for example. It looks like people are struggling with this. You'll find that hopefully 4 times 7 is 28. That's 1 mod 9, which means that 7 would be the inverse of 4. Does that make sense? Or are people still confused?
I just don't really understand this concept because I don't know where you got the 7.
Basically, the point is 7's the only one such that 4 times 7 is 1. Because like with like normal reciprocals, A times 1 over A is always 1. So you want to look for such a number. except you also want it to be an integer just so that it's easier to use. Yeah, William, basically inverse, yeah, basically like find some number, like for the inverse of A is some number B such that AB is 1. Inverses aren't always defined actually. They're only defined if the number that you want the inverse of is relatively prime to the modulus. Modulus as in the number you take the mod of. So for example, if you want the inverse of 3 mod 12, that doesn't exist because the greatest common divisor of 1 and 3, no, sorry, not 1 and 3, greatest common divisor of 3 and 12 is greater than 1. That makes sense because 3 times any number is divisible by 3 mod 12. Like 3, like even if you take it mod 12. This also means you can't divide by 3 in mod 12. So be careful with mods. Oh, more stuff in the chat. So Fermat's little theorem basically states that for any prime p, prime is important here, a to the p minus 1 is 1 mod p unless a is 0. So like, for example, 2 to the 4 is 1 mod 5 because Fermat's little theorem says so. There's an extension of this that's called Euler's totient function, which tells you that a to the phi of p is 1 for all relatively prime a and p. Phi, the Euler totient function, number of numbers under p that are relatively prime to p. So for example, we calculated that phi of 24 was 8. So if you take like 5 to the 8 mod 24, you'll get 1. Does that make sense? That's sort of a bit confusing. I recommend you should take notes. Yeah, this thing is called phi. Phi was, let me go back to 2 slides ago. This was phi. William, have you finished taking notes on that? Probably not now that I think about it. Yeah, okay, let's move on to okay, so here's a normal problem. Find the last 3 digits of 3 to the 1997. So does anyone have any ideas on how to do this? First of all, you see last 3 digits. What does that mean in modular arithmetic? Well, that means you just basically want 3 to the 1997 mod 1000, because when you divide a number by 1000, you're left with the last 3 digits as remainder. So how do we go calculate this? How can we use what we talked about on the previous slide? As a reminder, Euler's totient function stated that a to the phi of n, sorry, I should write a to the phi of p is 1 mod p. Can we use that here? Yeah, first of all, are people still following along? I'm worried that I might be going a bit too fast. No questions? Okay, does someone want to suggest? Well, first of all, if we want to use this Euler's totient thing, what is phi of 1,000 first? Anyone want to say what phi of 1,000 is? Anyone remember the formula for phi at least?
Anyone took notes?
Did anyone take notes on how to find phi of a number?
Also, the slides have been posted in Google Classroom, so you can check now.
You can always go into Google Classroom and check if you need to. Okay, William. We can go off of that now that I think about it. First of all, 1,000 has 2 prime factors. Those are 2 and 5. Now, oh my God. Okay, how many numbers below 1,000 are not divisible by 2? Just give me a fraction. What fraction of numbers below 1,000 aren't divisible by 2? One half, good. What fraction of numbers below 1,000 are not divisible by 5? Good, 4/5. And there's 1,000 total numbers. So how many of them are not divisible by 2 or 5? You just multiply this all out. That's 400. So that's phi of 1,000. Okay, back to the problem. 3 to the 1997 is 3 to the 2,000 over 3 cubed, which is 3 to the 400 to the 5th all over 27. Now 3 to the 400th is 1 mod 1,000 by this theorem, because 400 is phi of 1,000. So this is equal to 1 to the 5th over 27 mod 1,000. Okay, so that's 1 over 27. Now we need to find what 1 over 27 is. Some of you may know this. 27 times 37 is 999. This means that this is minus 1 mod 1,000. So 27 times minus 37 is 1 mod 1,000. And minus 37 is equivalent to minus 37 plus 1,000. That is 963. No, that's not true. That is 900. But yeah, that is 963, sorry. So those are the last 3 digits. And I'm starting to think I typed that wrong on the slides. Let me show the solution. Yeah, so this is basically the idea. Are there any questions about that? Okay, let's move on. Chinese remainder theorem. This one is, I don't know why it's called Chinese, but yeah, this is a very powerful but a bit complicated theorem. Basically, how do I describe this? Honestly, we might as well just go off of what this slide says. Let's say you have a bunch of relatively prime numbers, P through Z. And you have a bunch of A through C. Then you can find exactly one number that is equivalent to A mod P, B mod Q, etc. That is less than or equal to the product of all of these. So let me illustrate that with an example. 3, 4, and 5 are pairwise relatively prime numbers. So let's say we want a number that is 1 mod 3, 3 mod 4, and 2 mod 5. Then Chinese reindeer theorem tells us that there's exactly one number that's at most 3 times 4 times 5, which is 60. There's one number that's at most 60, that is all of these. So which would that be? That's 7. So that's the only number under 60 to have this property. The next such number is 7 plus 60, for example. Important to note, they do have to be relatively prime. Does this theorem make sense? I'm not seeing any questions. Give me a second, my parents are being loud in the background. Okay, yeah, I'm gonna assume there's no questions on this. It's a bit complicated, so I recommend you pull this up on your copy of the slides as well, so you can always refer to it. So here's an example of that. What's the third smallest number that's 1 mod 3, 2 mod 4, and 3 mod 5? Let me write those out so that you can see them side by side. So first of all, what's a pattern that you can see with all three of these? Does anyone want to know some sort of pattern they see? Dominic?
They each go up by 1.
Yeah. The equivalent way of writing that is each time the left number is 2 less than the right number. This means that we can write them as -2 mod 3, -2 mod 4, -2 mod 5. Now, can anyone think of a number that is -2 mod 3, mod 4, and mod 5? It doesn't have to be a whole number. Some number that's -2 mod all of these. I'm starting to think that I didn't explain mods well. Okay, what I'm trying to get at is -2 is -2 mod anything because mods, let's just say. So -2 satisfies all of these. It's not a whole number though. That's fine because if you remember 3 times 4 times 5, that's 60. So if we add a 60, that's 58. That's also going to be -2 mod all of these because you're adding a multiple of 3. So it's equivalent to adding 0 mod 3. You're also adding a multiple of 4 and a multiple of 5. So that's why. So that's the smallest one. For the third smallest, we just add 60 2 more times and get 178. So let me pull up the solution on the slides. Are there any questions about this one? Okay, I'll move on. Yeah, a lot of these I forgot the source of, but here, how many numbers below 1,000 are within 2 of, oh, sorry, I shouldn't say numbers. I should say these are all whole numbers, yeah. This means positive, basically. How many numbers below 1,000 are within 2 of a multiple of 7, a multiple of 11, and a multiple of 13? So does anyone have any ideas for this one? I'll tell you, this one's also sort of a combinatorics problem, but I think it's more number theory. It's like counting, sort of. But disguised within number theory ideas. So first of all, 2 within a multiple of 7. Which residues mod 7 satisfy that? Residue as in just like what number can go here? That is within 2 of a multiple of 7. Well, every multiple of 7 is 0 mod 7, so that definitely works. What are the numbers that are 2 within 0? Those are just -2 through 2. You can also write -2 as 5 and -1 as 6 because this is mod 7. Either way, you get that there are 5 different residues. Likewise, there are 5 different values mod 11 and 5 different values mod 13 that will work. What this means is that you have 5 choices for each, and what's nice is 7, 11, and 13 are prime, which means whatever choice of residues you pick, for example, you can pick 1 mod 7, -1 mod 11, and -2 mod 13. Chinese remainder theorem tells us we can always find a number between 1 and 1,001 that satisfies this. And exactly one such number. So 5 times 5 times 5. That's the number of choices of residues. So that's also the different possible, how many such numbers there are. So that gives us 125. That's not an answer choice. What are we missing here? Or in this case, what are we over counting here? You'll note that I said 1 through 1,001. What numbers are we restricted to? So which numbers are we overcounting? Since we're restricted to numbers below 1,000, that means that 1,000 and 1,001 should not be included in our count if they work. Both of them are within 2 of 1,001, which is a multiple of all 3 of these. So that means that we should subtract out each of those. So we have to subtract 2 from 125. That gives us 123. So that's our answer. Are there any questions about this one? Let me pull up the solution on the screen. Yes, everyone sees what I mean by this is more of a combo problem, like counting problem now, right? Okay, I'll move on. Here's another one. It looks very similar to a problem we already did. It's quite a bit harder though. Find the last three digits of 2 to the 1997. Okay, first of all, we know that phi of 1000 is 400 from that other problem. So what keeps us from saying that 2 to the 400 is equal to 1 mod 1000? Why does this not work? If you can't remember why, you have the slides on Google Classroom, you can go check them. I'll tell you, look for the, what was it called? Which page was it? Fermat's little theorem page and the one about modular arithmetic. Why can we not say that 2 to the 400 is 1 mod 1000? Now I can just put us back on the, yeah, Claire. They are not relatively prime. They share a common factor of 2, in fact. If you think about it, this is kind of silly anyways. This is trying to say that 2 to the 400 ends in 1. We know that can't be true. 2 to the 400 is even. Okay, so this isn't going to work. Then again, we just learned about Chinese remainder theorem. How can we sort of like split this problem? Instead of taking it mod 1000, can we think of 2 smaller mods that we can take that will both work out better? So basically the main idea is you want to group all the factors of 2 into one mod. That way the other mod you're free to use that theorem on. So let's start with mod 8. What's 2 to the 1997 mod 8? What's the remainder when you divide 2 to the 1997 by 8? Yeah, that's 0 because 2 to the 1997 is divisible by 8 because 8 is 2 cubed. Let's do it mod 125 now. 2 to the 1997 mod 125. So we know we can't use this quick, it's divisible by 125 anymore. But now that 2 and 125 are prime, I want to note we can use this theorem. 2 to the phi of 125 is 1 mod 125. So what's phi of 125? By the way, 125 is 5 cubed. So what's this phi of 125 then? 5 cubed, listen. Well, phi of 125 is just 4/5 of 125 because its only prime factor is 5. Yeah, Joanne, so it's 100. Sorry, William, I said cubed, not cubed, as in 5 to the 3rd power. Sorry. So yeah, 4/5 of 125, as Joanne says, is 100. So 2 to the 100 is 1 mod 25. Well, 2 to the 1997 is 2 to the 2000 over, this is going to look familiar, over 2 cubed. That's, this time we want to write it as 2 to the 100 all to the 20 over 8 and that is 1 to the 20 over 8 is 1/8 mod 125. Now we want 1/8. I'll tell you, if you want 1/8 mod 125, you don't want to guess and check every value. Instead, what you want to see is basically you can equivalently write this as 126 over. Give me a sec.
It's 15.75.
No, Siri, no, stop. Basically, 1 over 8 you can equivalently write as 126 over 8. Or adding another 125 to the numerator, 251 over 8, etc. So you can keep trying them. You'll see that I believe 376 over 8 is equal to 47. So 1 over 8 mod 125, that is 47. So you get that the number is 0 mod 8 and 47 mod 125. Okay, now let's put that together. Chinese remainder theorem tells us we can find a unique value mod 1000 for this. What would that unique value be? How you would calculate this is you just take 47 and then keep adding 125 until it's divisible by 8. So in this case, I believe you'll add 125 times 7 and you get 900, wait. No, wait, sorry. Give me a sec. Doing this too quickly. Sorry, you add 5 times 125 and you get 672. That you'll see is divisible by 8 and is 47 mod 125. So that's the value mod 1000 that we're looking for. That means that 2 to the 1997 ends in 672. Let me put that in text so that it's actually readable. Are there any questions about this? Yeah, this stuff is a bit complicated, but just takes some practice, I feel like. Yeah, that's like basically what I want to say is that modular arithmetic is really useful because you do not want to evaluate this value by hand. Even I do not have this high of a value memorized. And you will not have time to evaluate that on the test. So that's why using quick tricks with modular arithmetic is really useful. Okay, let's move on to, factorials and Wilson's theorem. Now this is what I should have put nearer to the beginning. So let's say you want to find the number of factors of 2 in a factorial. I should mention floor basically means the greatest integer below. That just in this case just means round down, actually. That's how I should describe it. So basically notice that about half the numbers are even, specifically half of them rounded down, because every other number is even. Each of those adds 1 factor of 2. A quarter of the numbers rounded down are divisible by 4. We've already counted them once, but they have another factor of 2 to contribute. Likewise, 1/8 of them are divisible by 8, which have yet another factor of 2, etc. So the full formula would be this. Okay, giving an example for that, how many factors of 2 are in 73 factorial? First, you take 73 halves rounded down, that's 36. 73 quarters rounded down, that's 18. 73 eighths rounded down, etc. So you add these all together and you get 70. So that means there are 70 factors of 2 in 73 factorial. By factor of 2, I mean like 2 to the 70 divides 73 factorial. This also works for other primes. Like if you want to find number of factors of 3 in 73 factorial, you take 73 over 3, round that down, add 73 over 9 rounded down, and 73 over 27 rounded down, etc. There's another neat trick relating factorials and modular arithmetic. Basically, for a prime p, p minus 1 factorial is minus 1 mod p. So as an example, 4 factorial is 1 mod 5, is minus 1 mod 5. This is true as 4 factorial is 24, and that is equivalent to minus 1. You also want to know that for other p minus 1 factorial is divisible by p unless p equals 4. P equals 4 is a special case, and it's also what almost got the number 4 completely banned in 2019 by some angry test takers. But that's for something else. Importantly, though, just if you ever see like p divides p minus 1 factorial, never forget to check p equals 4 separately. I believe this happened something on 2019 AMC10 as an example. What I'm trying to say is important. So usually you'll have a question that's like, how many zeros does this number end in? In this case, how many zeros does this factorial end in? Does anyone want to share how they do it? Well, keep in mind, I said the trick that I said only works for primes. So you're going to want to write 10 equals 2 times 5. And you can count the number of factors of 2 and the number of factors of 5 separately. I'll tell you there's always more factors of 2 than 5, so you only need to count 5s. Does anyone want to do the calculations and say what they end up with? Or does anyone want to at least type out what like the expression they would have for the answer? Well, you'll get, first you take 1337 over 5 and round that down. Actually, I think you'll know the formula, so I'll just have it written out. I'll tell you the way to calculate this formula quickly. Basically, you start by taking 1337 over 5 rounded down. Then instead of taking 1337 over 25, you can just also take this new value over 5, because this new value is already 1337 over 5. So 267 over 5 rounded down is 53. 53 over 5 rounded down is 10, 2, and then zeros. There's 332 factors of 5, and there are more factors of 2. So there's 332 zeros at the end. Are there any questions about that? Okay, here's another question. Find the remainder when 40 factorials divided by 1763. I'll spare you the trouble and tell you that 1763 is 41 times, oh, I'm writing in white, whoops. 41 times 43. So first of all, what ideas will we probably end up using? Since 1763 isn't prime, we'll probably want to split the problem into 41 and 43 and put it back together using Chinese remainder theorem. Since we see a large factorial, we're probably also going to be using something like Wilson's theorem or that trick I mentioned earlier. So let's split the problem into 40 factorial mod 41 and 40 factorial mod 43. Now, what's 40 factorial mod 41? Who remembers Wilson's theorem? Does anyone have Wilson's theorem written down? If not, you can always pull it up from Google Classroom. And what does it say about this? Claire has a good point. The Google Classroom copy does have all the answers. That is unfortunate. Oh well. 40 factorial mod 41. By Wilson's, that's -1. Remember that Wilson states p minus 1 factorial is -1 mod p for prime p. In fact, that's why we split into primes in the first place. 40 factorial mod 43 is not as easy. We know 42 factorial mod 43, so let's try to get it in terms of that first. So right, 40 factorial is 42 factorial over 41 times 42, which this 42 factorial becomes -1, as we know. In fact, we can also write the 41 and 42 as -2 and -1 because this is mod 43. This way you don't have to deal with multiplying by such big numbers. This equals -1/2. And that equals 20 mod 43. Because the inverse of 2 is 21. That's not true. The inverse of 2 is 22. And so negative that would be 21 mod 43. So you get -1 mod 41, 21 mod 43. You splice those together with CRT. I don't feel like going through that again. So I'll bring up the text solution and you get that the answer would be 1311.